See the shared screen.
Good afternoon, sir.
Okay. Okay, fine. So in the last lecture, we discussed about range equation, okay, where we derived the equation for how the power received at the receiver is calculated in terms of transmitted power and parameters associated with the laser footprint, laser transmitter, receiver, as well as atmospheric properties. Okay. Then after in the previous lecture, there was discussion on densities estimation along the scale line as well as across the scale line in case of oscillating mirror scanning pattern. Okay, so scanning pattern that we obtain using the oscillating mirror that is inbuilt with the laser scanner unit. Fine. So in today's session, we are going to talk about types of ranging principle which are there in case of LiDAR. Okay. So we'll discuss one by one. We have two types of range estimation process. So types of ranging. So you are already aware about meaning of ranging over here. This is the procedure by which distance from laser transmitter. This is the laser source. It is a laser transmitter. Okay. So this distance from laser transmitter to the target point P, it is measured. Okay. And how it is measured? A laser beam is transmitted laser beam. It goes from laser transmitter to target point P. Okay. And then further it returned back. Okay. So this is the this entire procedure is called as ranging. And this is realized basically by measuring the total time of flight. As I discussed, time of flight, TOF. We also call it total time of travel. And it is a distance that is by laser pulse. This is laser beam. Now, how we define the laser beam? Okay. So the pulse laser we have already discussed. How many types of laser beam can be generated by the laser source? Okay. So the first one is, if I say this is pulsed laser. Okay. And here you have already seen that at a certain interval, a laser pulse is generated by the laser source. And it is plotted time versus amplitude. Second category is continuous wave laser. Okay. So in the continuous wave laser beam is transmitted in the form of sinusoid, a cosinusoid. Okay. So it's A time T and it is A sine omega T, this graph. Okay. Using pulsed laser, It is basically on the basis of measurement of total time of flight uh, that is taken by a laser pulse from laser source to target point P and back to the laser source. While in case of continuous wave laser, we do the phase measurement. It is on the basis of phase measurement. We'll discuss it in very detail. Okay. How on the basis of phase measurement, the distance can be calculated. That is d over here using the continuous wave laser. Okay. Fine. So in the pulse laser, we have already seen that this time TL that is calculated. This time TL can be written as 2 R by C. TL is same as time of flight. Okay. So time TL, it is corresponding to a laser pulse. It is equal to 2 R by C. So obviously we have, if you simplify it, so the range, that is distance d over here, is equal to TL divided by 2C. Okay. Now one parameter we estimate over here in case of pulse laser, that is range resolution. Let me add another slide over here. So the time range is equal to TL divided by 2C. We define a parameter that is range resolution. So range resolution is calculated as delta R. It is equal to 1 by 2. Okay. I think this should be C is coming into the multiplication. Please correct it. C into TL by 2. Okay. So 1 by 2 C is the constant, and that is delta PL. Okay. So this delta R is termed as range resolution. Okay. And the range resolution is directly proportional to the time resolution delta TL. So this time resolution is related with the counter circuit. Do you know what is the meaning of resolution? Anyone can
So the extent at which we can differentiate between two features.
yeah, let's say a scale is given. Okay. For the distance measurement, if you are using a scale, okay, so you can notice on the scale that is there are the marker, is it? Okay. Now this is 1 centimeter. Okay. So how many blocks we have? 10 blocks we have. Okay. So let's say if you are doing the measurement and that point is coming in between this over here. Okay, but there is no marking on the scale to measure this point. So either it is measured just before that or just after that. So if we divide 1 centimeter into 10 parts, then what it will be? It will be
1 mm.
tenth of 1 centimeter is 1 mm. Okay. So if you write over here, it will be 1, 2, 3, 4, 8, 9, and this will come 10. Fine. So 1 mm will be the resolution of this scale. This is the meaning. Because if your measurement, any measurement from, let's say, this is the point P1 and to point P2, you are doing the measurement, but one you place at 0, scale 0 marking will come over here at P1, and at P2, let's say it is coming in middle. This is mm mark, and this is the next level of millimeter. If it is coming in middle, how you can do the measurement? You are not sure. Okay, so this is meaning this scale has the limitation in the measurement, and it is defined in terms of resolution. Okay, so resolution of the scale is 1 millimeter. Similarly, in this case, delta R. Okay, so delta R is the range resolution. What does this mean? Let's say this is the laser source. Okay, and from here we have a point P1 somewhere. Similar concept of this scale is applied over here. How accurately point P1 is recorded? This distance, let's say this is origin O, this is point P1. So how accurately DOP1 is recorded? Okay, so delta R gives us idea that, let's say if this is lying between this and this is the delta R. Okay, so this is the resolution, like this P1 could be the range, this distance could be anywhere over here. This delta R is the range resolution. So this is a limitation of this instrument. So this delta R is dependent on delta TL. Obviously, it will be delta TL. Like when your receiver receives the signal and quickly it is giving trigger signal to the counter to stop the counting, what is the resolution of counter circuit? Like in your clock, the second, like this second moves. So the clock has a limitation. Okay, like that is 1 second. Because once you don't have a further, like this is some indication in microsecond or millisecond. So similarly, the counter circuit has its own resolution, time resolution. Like if two signals are coming, so they are assigned a particular time. Like, okay, at this time, this return is arrived at the receiver. So there is a time resolution of the counter circuit. In that way, the counter does the counting. So delta R is dependent on delta TL. Okay, tell me, let's say if we want to keep delta R in the range of, let's say, 5 centimeter. Okay, we are comfortable with 5 centimeter range resolution. Then what should be TL in that case? What should be the resolution of counter circuit? Do the calculation and let me know.
9 nanoseconds.
How many nanosecond? Calculate, tell me the exact figure. So in that case, just substitute delta TL. It is equal to 5 centimeter. So convert it to in the SI unit form. Okay, 2 into Is it fine? So it will be
The 3.33 microseconds.
yes, microsecond.
Yes, sir.
It will be nanosecond.
Yes, sir. Sorry, sir. Nanoseconds.
10 to the power minus 9, sir, nanosecond.
It will be कितना आएगा?
Sir, 2 times delta R we should take, na sir. Delta TL equals to 2 times delta R divided by velocity.
That is taken, just see on this screen.
Sir, 0.33 multiplied 10 to power minus 10.
0.3 nano, sir.
Okay, fine. This will be multiplied over. Is it?
2 should be multiplied numerator.
Correct, correct. It will be 10. So 1 by 3. Fine. It comes out to be 1 by 3 into 10 to power minus 9. Is it?
Yes, sir.
Yes, sir.
Yeah. So 10 by 3, it comes out to be 0.33 into 10 to the power minus 9. So 0.33 nanosecond. Just see the level of resolution that is needed over here. That counter circuit should be able to differentiate even the difference of 0.33 nanosecond. Okay, this is the reason why the level of accuracy we want to achieve using the laser scanning system. These instruments are very costly right now. Though there is advancement in technology and other aspect, business aspect also comes into the picture. So we expect due course of time, the instrument would be cheaper. Okay. So, okay. So I hope you have understood the meaning of range resolution, time resolution of counter circuit over here. Is it clear? Okay. So what is the inference from this discussion? The most important aspect is how accurately the laser scanner is recording the time. Okay? Because even the deviation of 1 nanosecond, okay, lead to error of 15 centimeter. Okay, so we'll see what kind of concept is used for the sensing the laser this return signal, as well as at what point the receiver unit is triggered to stop the counting. So before discussing that part, first we'll see what is the shape of transmitted laser pulse, and once it is received at the receiver, what kind of changes are occurred in the shape of the laser beam, that is laser pulse. So we'll see one by one. First, we consider the ideal case. Let's say the Gaussian shape, it is shape of transmitted laser pulse. Okay. When it interact at a particular point, let's say P1, So this is transmitted. In ideal case, it is reflected back, and yes, I will plot the shapes of return signal from the various surfaces. Okay. In ideal case, what I'm considering, like there is no change in the shape, only there is decrease in amplitude. Okay. Let's say this amplitude is somewhere a max. What it will be, shape will not change. It will be AM into this reflectance. Fine. So it is multiplied by the reflectance into maximum. This will be in ideal case, but generally the shape of return is not same as the shape of transmitted. What happens, like when let's say this laser pulse is interacting with the flat target. This is flat target. So it interact and reflected back. Okay. From the flat target, the amplitude will decrease. The shape will not be distorted much. As what happens? Let's say at this point, interaction starts. Okay. Till this point. So once let's say this is time, it's a T2 and this is T1. Okay. So in this case, T2 is considered as T2 is previous than T1. So T2 will first interact over here. Then last interaction takes place at T1. Okay. So the entire shape of this laser pulse interact between T2 and T2 and T1. So what will happen? The T1 and T2 will be same. The pulse will not elongate. I hope you are getting the point. The pulse will not elongate. Okay. Only there will be decrease in amplitude compared with I will later let you know why I am interested in the distortion in the shape. Compared with transmitted, the T1, T2 will not change, but there will be decrease in the peak amplitude. Fine. Okay. Now let's say if there is a building. Again, it is flat. So, and this is the laser transmitter. Please make note on this because this concept you will not get in any reference note. So what happens? Why this is conical? Why not cylindrical? When this laser be, if this laser pulse start emanating from this transmitter. Okay. So why it is in conical confinement? Why not in cylindrical confinement? The laser energy is progressing towards target. Arun Kumar Sahani, could you please unmute?
यस सर।
बताइए।
सर क्योंकि जब पल्स फायर होगा सर और जहाँ जहाँ से इंटरेक्शन होगा तो वहाँ से जो रिफ्लेक्शन आएगी सर उसकी वजह से शायद ये कोनिक।
Please listen carefully. When this is the circular aperture of laser transmitter, from the circular aperture, this previously it's an electrical signal. Now this entire shape, it is leaving the surface of transmitter, that is antenna over there. So when it is a signal, and it progresses towards target, why not only within this cylindrical confinement? Why it is dispersed?
सर ड्यू टू स्कैटरिंग समथिंग।
समथिंग नहीं, क्लियर बताइए आप, पढ़ाया गया है इसको।
ड्यू टू स्कैटरिंग सर।
Are you sure scattering happens?
Yes sir, scattering.
Please revise it, okay? I suggest you to go through the previous notes and videos and see that. चलिए म्यूट करिए अपने को। सुमित।
Sir, that is due to diffraction.
Correct. So what is how we calculate a diffraction angle alpha? This is due to diffraction.
So that is 2.44 lambda upon dt.
Correct. 2.44 lambda divided by
dt,
where dt is the transmitter diameter. Correct.
Yes.
Okay. So though this is not a part of discussion, see, due course of lecture, I will also take up the concept which we have already discussed previously, so that there will be revision as well. So this is the reason why we have a diffraction. Due to the diffraction, there is a deviation and dispersion, and that leads to the larger size of laser footprint compared to dt. Okay. So we can say that the d footprint is always greater than dt. Why? Due to alpha diffraction. Okay. So our main objective over here, just see if this is the building, both surfaces are flat over here. This is the roof part and this is the adjacent ground part. Now see what happens. Again, it is represented by T2 and this is represented by T1. This energy is confined, entire energy is confined within this. Okay. But see over here, this part of energy is also interacting in this region. Okay. Though it is flat, okay, so interaction takes place between T1 and T2. And one return you can expect from here. Okay. Now, rest of the energy is interacting from ground part. So another return you will get from here. I hope it is clear. So second we plot over here, that is in case of building wall, it's a multiple return. Okay. So very weak signal. by analyzing these two return, can we able to measure the height of the building? Let's say we have two returns. See carefully. At two different building locations, this return we are getting 1 point from building B1, and this is from building B2. If you analyze these two returns, obviously two return we have, one from building top, another from building bottom. In which case height of the building is highest? Building B1, in which case the height of building is more, in case of B1 or B2?
B2.
Why B2?
Sir, because it is taking more time lag between two pulses.
Correct. So if you see over here, if you increase this height, then what will happen? Gap between these two will increase. See, I have been discussing with the pictorial representation, and it is very easy to understand. As you can see in this figure, one return we are getting from the first interaction, second return we are getting from here. Okay. If you increase the height of the building, then what will happen? Time gap between these two pulse will increase. Okay. So you can say that height of B2 is more than height of B1. Okay. Fine. Now the next case. Let me add a new slide. Laser source, transmitted laser pulse. Okay. Now this is inclined surface. Again, interaction T2 and T1. From T1 pulse start, T2 pulse end. What kind of return we get? If we make it this is the cylindrical confinement. Okay. But we have broadening. There is a what kind of return we get? If it is flat, one case. It's not flat, it is deviated by angle theta. Can any one of you draw it and can you share with me? I have given you option to share a document from your side. I hope the question is clear to you, and I expect you have written it in your notebook. Now I'm giving the option. Write the shape, just draw the shape of return signal and present over here. Just you can share your file. Take your time. I'm giving you, let's say, 6 to 7 minutes. Do it, then we'll discuss. Okay, so what is the status? Any one of you have solved it? Vibham, could you please unmute?
Yes, sir.
Have you done it?
Sir, I have tried. Uh, will the peak between the distance between the peaks will reduce?
No. Can you share your document if it is possible?
Uh,
Okay. Anyway, let me discuss. Okay.
okay.
Okay. Just see what happens. This entire pulse energy will be distributed. Fine. In this conical confinement, entire. Okay. Now see what happened when this laser pulse progresses. Let's say this is T2 and this is T1. And this length in the space will be how much it will be? dT1 T2 is equal to C into T2 minus T1. Okay. The first interaction will be over here. Okay. And this interaction will go from T1 to T2. It will be delayed. At this point, interaction will be from T2 to T1. Okay. But see, at this point, T2, T1 will end, but the time should be taken. When this pulse, when this, the first, we can say this, the forwarding edge. The forwarding edge will reach this point after time, let's say this distance, T naught. Okay. So interaction at this point will be earlier, then further it will be delayed. It will be delayed by D naught. So what will happen? The return shape will be elongated. And how much it will be? T2 minus T1 plus T naught divided by speed of light c. So in this case, when there is an inclined surface, okay, and even see the footprint will also be, the diameter of footprint will also increase. Okay, let's say if this is df and this is angle theta, so how much it will be? This point A, B, and C. What will length DA to C? It will be equal to df divided by cos theta. Okay, and this will be elongated. This will be T2 minus T1 plus roughly, I'm just writing. So this total spread, let's say T naught. So this T naught is proportional to T2 minus T1 plus D naught by C. So what happens in this case? If it is interacted with the inclined surface, then This is the transmitted pulse. And the shape of return will be like this. Okay. Now, what will be the challenge? Why we are discussing the shape of return pulse? Okay. In the previous case, we have derived that the delta range resolution is equal to C by 2 into delta TL. Okay. And we have seen that this is very crucial parameter. We want to keep it very low. Okay. Now this is transmitted laser pulse and this is received laser pulse. Time t, this is amplitude. Transmitted, this is amplitude received. Okay. So when this pulse emanates from the transmitter, when this pulse starts emanate from the transmitter, at which point we generate a signal to the counter to start the counting. Because see, this length is T2 minus T1. Let's say this is T2 and this is T1. Okay, generally we consider this TP. The pulse width TP is around 10 nanosecond. We want to keep it very low. So if this is 10 nanosecond means, what is the distance in 10 nanosecond? How much distance is covered in 10 nanosecond?
3 meters.
Meter.
Just see 3 meter. So this distance is, if you convert this time, this distance is 3 meter. So our concern is at which point the signal has to be sent, at which point we have to send the signal to the counter circuit to start the counting. Somewhere here we have a counter circuit. Okay. So this counter circuit start counting the time of flight, the time. Okay. So at which point, and once if such kind of signal is received, and this is a broadened signal, at which point we send again signal to the receiver. This is a stop signal. Okay. From where we set start signal. Okay. So because see, if we are sending at particular time location, the start signal, at the same location corresponding to the return signal, we send the stop signal. Is it fine? Okay. So there are various ways to do it. So how to measure time of travel? Okay. We discuss over here the constant fraction. The constant fraction method. Okay. In this method, what we do, with respect to a specific point on leading edge. This is the leading edge. Okay, so the first, just see the analysis. So what we do with respect to a specific point on leading edge, we generate a trigger signal to initialize the counter circuit. Okay, so the time counter is started by a transmit pulse. Okay, and time counter stops when voltage reaches a predefined, pre-specific value for a received pulse. So what we do, we define a specific voltage level. Okay, let's say this V threshold. We define a voltage threshold level that is generated at a certain level over here. Fine. And at the rising edge, when it intersect at this point of time, trigger signal is generated. What is role of trigger signal? To start counting. And it is used to initialize time counter, and it is initialized. Okay. Now, what we do at the same VTS level, received signal at the same VTS level on the rising edge, that is rising edge, somewhere here, and this is level VTH. Again, a signal is generated I hope you can see the shared screen.
Yes, sir.
Okay, fine. So what happened? Again, a trigger signal is generated over here. To what? To stop counting. Okay. Stop. Okay, got the point? What will be the problem in this case? Just see, at a varying level of reflectance, this shape could be like this. It could be like this. But see, due to change in shape, the point in the intersection point differs. In this case, stop, while in this case, and in this, so the time at which we need to generate a stop signal differs with respect to change in the shape, change in the shape of return waveform. Okay, and the change which you can notice over here, that is okay. So just these are the differences you can notice. Okay, this is called as range walk. Due to change in shape of the return waveform, the range measurement is walking, like it's increasing, keeps on increasing. Okay, so I would like to quickly summarize the entire process. How to measure time of travel by using the constant fraction method. It means with respect to the maximum amplitude, we define a level. Lower than that, that is represented by VTH over here. Okay, and at the specific point, that is intersection point of VTH and waveform, from the leading edge, a trigger signal is generated to initialize the counter, time counter. Okay, so and at the same level, the returns further that we define. Even this threshold level could be changed in case of signal received. Okay, but whatever the strategy that is adopted for generating a stop signal in a constant fraction method, it is fixed. Once we have set a threshold level, it is fixed irrespective of the shape of return waveform. So what happens from the same point? Let's say if you change the material property, if its reflectance, its topology changes, what happens? In that case, time at which we need to send a stop signal varies. Okay, and that is further leading to the inaccurate measurement of range, and we call it range walk. Okay. So again, if I would like to plot over here, just see. This transmitted pulse. And somewhere here we have received it. Okay, and let's say this is the threshold that we have decided. And here we have decided a threshold. And at the rising edge, okay, we are sending the stop and start signal. So what happened? This is time axis. This is also time axis. From this point onward, let's say t is equal to 0. Counter, start counting. Okay. Now for this pulse, stop. Here also stop. So just see what we notice. In the first case, this is the range. In the second case, range increases, while in the third case, range further increases. So this is called as range walk. Now let me know if there is any query in this discussion. I'm giving you 5 minutes time. Please go through the discussion and let me know if there is any doubt. Okay, so let me know, is there any doubt?